Hi guys, I just wanted to quickly talk you through root mean square error, which is something that we've looked at earlier in the course. And it's basically a tool that helps us make a decision about how good our model is at predicting outcomes, which of course is one of the main reasons that we create the models in the first place. So we use root mean square error as a way of assessing how far away from reality our predictions are. So it's really the case that we're going to be using it where we have a model, we've developed the model and we've trained the model, and then we've fitted the model, and by that I mean we've tried to make sure that it's not just good at predicting things in the training data, but will actually, as far as we can tell, be useful in the real world. And then we're probably at the stage of running it against our test data, and that's the first chance that we get to try our model out basically in the wild. So we've had a model that's been working well with our training data, but how good does it perform out there in the real world? And that's what root mean square error helps us with. One of the important things to remember about root mean square error is that the number it gives you at the end of the process isn't just an abstract term. It's actually in the units that we're measuring. So whichever phenomena we're measuring, the number that we get from the root mean square error is actually in that same unit. And that's really useful because if we're talking about measuring something in terms of dollars or krona or British pounds or kilos or meters or microns or whatever it might be, root mean square error means that we have a language that we can talk about that in that will be recognizable to other people. So I'm just going to get some paper and we'll talk through an example of what it looks like and how we calculate it. Okay, got some paper, and as you can see, as if by magic, we have something on the paper. Right, root mean square error then. Well, what are we talking about? Well, ignore the root bit at the beginning. That just basically means that we're getting back to a number that's in the same size as the phenomenon that we're looking at. So we do that because we're doing this. When you square something, you end up with a much bigger number. You multiply the apparent size of the gaps, the differences between the real and predicted values, and it's not in the same terms as the thing that you're actually looking at. So squaring things is good for getting rid of the negative numbers that I'm about to talk about, but you need to take the square root in order to get back to the same term as you're looking at. If we look down here, this is what I'm talking about. We've got a simple linear regression model here, and they of course are very popular in machine learning because in machine learning we often do a simple thing very many times. And that has proved to be a much more powerful technique than doing something less often, but it's much more complicated. So simple linear regressions are very popular in the machine learning world. And what we have here is a typical example of that, where we've got independent variable along the bottom, dependent variable along the sides, and then we have these units here, this 5, 10, 15, which could be anything, but let's say that they're kilos. And the things along the bottom are sizes, say bags of potatoes or something silly. Okay, so the blue line then, what we've got with the blue line is our predicted values. So what our model is doing is it's giving us a set of predictions. And these predictions have been produced as a result of the training set that we've run the model over, and then we are basically at the stage of thinking about whether that matches what we see in the real world. And what we've got from the real world are these data points here. And what we've got with the pink line is an example of one of these residuals. The standard deviation of the residuals, which is another name for root mean square error. But residuals, error, is the same thing. Error can be a little bit misleading in this sense because it doesn't mean it's a mistake, it's just literally referring to the size of the gap between what we observed in the real world and what we predicted at this point with the model. And what we want to do really is to make sure that we have as lower number as possible as our prediction. And if we can do that, then we've got a model that's acting in the way that we would like it to. It's providing us with good quality predictions. If we've overfitted the model so that it perfectly predicts the training data, then we might find that instead of having this sort of narrower dispersal of data points that we have here, we could have data points all over the place, and then our model wouldn't be so good. So let's have a think about how we calculate this root mean square error. So it's simply a tool that gives us a number. The number is done in the same terms as the phenomenon we're looking at, the thing that we're modelling, and we calculate it basically through the means of a simple equation, and I'm just going to talk through that with you a little bit. So what's going on here then? Well, what we have here is the things that we've actually seen in the real world, this term y, and y with a little hat on it. This is the thing that we predicted, and this is the gap. So we have the actual value that we saw, we take away our predicted value, and we'll end up with a number. The I here is an index. It represents the current item being looked at, because we need to have a look, when we're looking at all of these data points, we need to have a look at all of them, not just one. So all the I is like a counter. Now we need to get rid of any negative signs, so we square the values, and by squaring the values we'll get rid of negative signs. And then what we want to do with those is, once we've got them, we want to add them all up, and the way we represent that idea is with the capital sigma, and then we have these other two little bits added to that. So this is, we're just going to sum all of these squared differences, and the n just represents the number of items that we've got, the number of data points that we have. So n often represents the number of data points, and I equals 1, that just means we're starting at the beginning of the series. And then what we need to do is we'll then divide this by the number of observations, and then we'll take the square root of that. So going back to our original simple example then, we've got different data points, we've got a gap. If we take these gaps, say this is a gap of 1, and then we square it, let's stay with 1, but if we add up all of those gaps, and just for the sake of argument, so we end up with all of the squared values adding up to 16, and we've got, I'll just make it easy, I can do this in my head then. So we've got 4 observations, so 16 divided by 4, that equals 4 of course, and then if we take the square root of 4, we'll get the number 2. So what we've got there then is an RMSE value of 2, but 2 what? Well, 2 of whatever this is, and in this case we said it was kilos, so we've got a difference of 2 kilos, and that means that our prediction is likely to be 2 kilos more or less than the actual observed value. And if you remember, and one of the reasons this is the standard deviation of the residuals, we think about one standard deviation either side, so that's 95% of values. We would expect 95% of values to fall into this range of being plus or minus 2 kilos. So this feels like a model that's actually doing quite a good job. You can't say for certain, because you need to know what the rules are for your particular application. So the lower the number, usually the better, but it could be that in this situation we actually need to have a model that is sensitive enough to not have an RMSE above 0.5, for example. So we might say, well, it's not so good. But in this situation, it feels like a pretty good model, because the line is quite close to all of the observed data points. If all the observed data points were up here and sort of miles away from the line, then we would say that the model wasn't quite so good at doing what we wanted it to. But this feels like a pretty good model. So root mean square error is just a tool for looking at the usefulness of our own model as a predictor. It's quite a straightforward calculation. We just take the sum for all of the observations. We take the sum of each individual observation compared to the actual value that we saw, the predicted value compared to the actual value that is there at that point. We square it in order to get rid of negative signs, so we're only dealing with positive numbers. We divide by the number of observations, and then we take the square root of that number so that we are going back to the original units of measurement. So RMSE sounds really complicated. The libraries that we're using will fix all the calculations for us, so we don't have to do all of them individually, and it's just a useful way of identifying whether our model is predicting things successfully in the real world. Okay, so I'm going to go and make another video about some of the other measurement tools.